All right, so I'm going to apply the fundamental theorem of calculus to the net change theorem. Now, the net change theorem is very, very similar to the fundamental theorem of calculus, but you have to remember one thing. And in this case, I'm going to do a definite integral from a to b of f prime of x dx. And what you need to know here is that f prime of x is describing a rate of change. Now, that's an important thing to remember from Calculus 1 is that's the thing. All derivatives are describing the rate of change of some other function. And so that's what we're doing. We're talking about the rate of change of some function. And so what we're going to do is we're going to get that function back out and we're going to find what would be called the net change. That is, if we take a rate of change in a definite integral, we're going to find out how much it changed overall. So I'm going to apply that to a specific problem. In this case, a developing country consumes oil at a rate of R of t equals 20 times e to the 0.2 times t million barrels per year. Now, notice that may not be written as a derivative, but it still says it's a rate of change. So I'm still going to do the net change theorem here. And what we're looking for is, again, t is measured in years from 0 to 10. How much oil does that country consume during those 10 years? So again, we have the rate, and we want to know how much change there was over that time. So again, we're going to do a definite integral here. Now, we're talking about a total of 10 years. So I'm going to go from 0 to 10, and I'm going to plug in my rate of change. So 20 times e to the 0.2t, and I'm going to use dt here because our variable is t. Now, hopefully you guys are thinking in your head, we're learning our rules of of definite integrals or of integration in general. And so when we have this exponential function, we're going to want to try to do a little bit of that u substitution here to this exponent to make it just that variable. So what I'm going to do here is I'm going to use a u substitution where u is 0.2t. In case you want to write that as a fraction because it might actually help you in the end, that's 1/5 of t. Now, what we're going to do now is we're going to take this u, find the derivative of it, and apply u substitution. So du is equal to just 1/5 of dt. So if I want to switch out this dt for a du, that's actually going to be 5 dus for that dt. Now, the other thing that I want to point out, and it's kind of important for you to remember, is you see these original bounds of integration. I have to, again, use that u substitution on them. So if t was originally 0, that means 0.2 times 0 gives me u is 0. So that's going to be my lower bound. But at the same time, if t is 10, 0.2 or 1/5 of 10 is 2. So I'm going to change my new my definite integral to have a new bounds in terms of u. So in this case, we're going to go from 0 to 2 instead of from 0 to 10 of 20 times e to the u, and I'm switching out that dt for 5 dus. Okay, I'm going to go ahead and multiply these essentially coefficients together, and I'm also going to take it out front. So 20 times 5 makes 100. So I'm going to go ahead and pull the 100 out because it has nothing to do with u, and I'm going to integrate from 0 to 2 of e to the u du. Now again, you guys are learning your rules for definite integrals, so if you have an exponential function, e to the whatever, as long as it's just that variable, it's going to stay that variable. So we're going to have 100 times e to the u evaluated from 0 to 2. Now, all I've got to do at this point is plug that stuff in. So we're going to have 100 times e to the second minus e to the 0. E to the 0 is just 1. So we're going to have 100 times e squared minus 100. Now, here's the thing. If you want to leave it like that, that is completely okay, because here's the thing. This is an exact answer. If you want to know the approximate answer, you can plug it into the calculator. On 100, e squared minus 100 leaves me with 638.91 approximately. And that's, like I said, approximate answer. Let's be honest, we'd rather have the exact answer. And so that's how we're going to do this. Hopefully that made sense. If not, ask me any questions you got.